Today we're going to talk about C2 and we're going to look over part 1 of C2, which is the rate and extent of chemical change. On the screen in front of you, you can see a tick list of all of the statements for the first part of this module. Now, in these tick lists, you can see that some of these statements are highlighted as higher tier only, and some are highlighted as triple science only. Today, we aim to get to the bottom of statement number 9, which is talking about dynamic equilibria. So first of all, let's look at what rate is. Well, these 3 questions are here for you to have a little think about. Now, feel free to pause this video now to have a discussion about what these 3 questions mean. Alternatively, you can write them independently. Now, rate describes the speed at which something happens. And normally when we talk about rate, we talk about something happening over time. Where we talk about this in terms of a rate of a reaction, we're looking at the rate of a reaction moving to completion. And how we measure that can be in a couple of different ways. So firstly, we can talk about rate of reaction being how quickly the product is used up. So what you can see on the diagram in front of you is these small yellow boxes. These represent your reactants, your starting materials. Now we could measure the rate of reaction by looking at how long it takes for those reactants to be used up. Alternatively, using this exact same setup here, we could measure the rate of production of gas and how much gas is collected each minute. And eventually we'll be able to see the point at which the reaction is completed when there was no more further gas produced. Now let's look at how we calculate rate of reaction. Now there are 2 equations that we can use that I have alluded to previously. So mean rate of reaction can be defined as either the quantity of reaction used divided by the time taken, or the quantity of product formed over the amount of time taken for this to be formed. Now these 2 are mean rates of reaction. I will talk to you in a bit about how to work out the specific rate of reaction at a given point. Now what is rate of reaction? Before we talk about a reaction, we must first talk about collision theory. Collision theory dictates to us what and why things react. So chemical reactions can only occur when reacting particles collide with each other with sufficient energy. Now, it's important to note that particles collide with each other all the time. They are constantly moving, particularly when in gas form, and they're constantly bumping into each other. But not every single one of these collisions results in a reaction. In fact, only when they have sufficient energy is there a possibility for that to happen. And we call that sufficient amount of energy the activation energy. It's the energy required for things to react. So let's look at how we can vary the rate of reaction, how we can increase the rate of reaction in order to use it in our own chemical reactions. How can we increase our rate? Now, first of all, let's talk about temperature. So here you can see a little graph that shows what we mean when we talk about how increasing temperature increases the rate of reaction. You have 2 curves here. Now, the first curve shows you particles at a lower temperature, and the second curve shows you particles at a higher temperature. Now, the A on the x-axis shows you the point at which that you have reached the activation energy. So everything to the right of that point are particles or proportion of particles at or above the activation energy. Now, at a higher temperature, particles are moving more quickly. They're colliding more frequently and they're colliding with more energy. So what you see is a greater proportion of those particles are at or above the activation energy. And if a greater proportion are at or above the activation energy, then that means you're going to get a higher rate of reaction. What I would like you to do now is to pause this video, and I would like you to write an explanation of why increasing temperature increases your rate of reaction. When you come back, I will show you a model answer. So, an answer that you could use here, and apologies for the change in font, is that when you have a higher temperature, you increase the thermal energy store of those particles, which means that a greater proportion of particles are at or above the activation energy. Therefore, you have more successful collisions and a higher rate of reaction. Particles are colliding with more energy. Now, the second one I want to look at with you today is surface area to volume ratio. Now, here we've got two diagrams that show this really clearly. Surface area to volume ratio is about how much of the outside of a substance, how many particles on the outer surfaces of something are exposed to react in comparison to its overall volume. And on the whole, when we're looking at increasing surface area, we are talking about chopping things up into smaller pieces. Overall, the volume is the exact same. I can chop things up into smaller and smaller pieces, but I can still keep the same volume despite the size of those particles. The surface area, though, increases because as I chop things smaller, I'm exposing more particles on the outside of each of those smaller surfaces, which means they can react more. And this second diagram here shows that really, really well. Now, but when you've got more particles exposed to react, you're going to have more frequent collisions. And if you have more frequent collisions, you are going to have a faster rate of reaction. More collisions means a higher rate of reaction. Now, it's important, really important, that you use the word frequent. If you say just collisions, it doesn't quite get across the right answer, because collisions in a given amount of time is what we're talking about, not just in general collisions. So it's all about the frequency, how often those collisions are taking place. So that's surface area to volume ratio. With a higher surface area to volume ratio, you get a faster rate of reaction. I'd like you to now do the same thing as before. I would like you to write a model answer in your books or on a piece of paper to explain why higher surface area to volume ratio results in a higher rate of reaction. Pause the video now. What you should have done now is come up with an answer very similar to this. A higher surface area to volume ratio means that there are more particles available to react at any one time. This increases the frequency of collisions, which then increases the rate of a reaction. Now, hopefully you're starting to realise that there is a pattern to the way in which we answer these questions and how to get full marks on them. Ideally, normally, they're about 3 marks. Sometimes they can be fewer, sometimes they can be 2. And on occasion, they can be 4 marks when there is a greater level of depth needed. So let's move on to some of the shorter ones. Let's look at pressure. So on the diagram here, you can see 2 different scenarios. On the left-hand side, you can see a container where there is more space, but the same number of particles. And on the right-hand side, a container where there is less space, but again, the same number of particles. The difference here is not the size of the container, although I know that is a difference. What we're looking at here is the distance between particles. On the right-hand side, at higher pressure, there is less space between particles. This means that there is a higher chance that those particles are going to collide, and so what we say is that there is a higher frequency of collisions. More collisions means that we have a higher rate of reaction. So again, pause the video now, take a couple of minutes to write down a model answer for why higher pressure results in a higher rate of reaction. Your answer, very simply, higher pressure means that there's less space between particles. This increases the frequency of collisions and increases the rate of a reaction. Moving on to concentration, which is very, very similar to pressure. But normally with concentration, we're talking about solutions. So it could be solids dissolved within liquids. It can be 2 liquids dissolved together. On the diagram, you can see on one side, on the left, you've got the low concentration. And on the right-hand side, you've got high concentration. Now, with a higher concentration, there are more particles per unit volume of solution. And what that means is, in the same volume of solution, there are more particles available to react. If there are more particles per unit volume, then you're going to have an increased frequency of collisions and therefore a higher rate of reaction. Pause the video and tell me why having a higher concentration results in a higher rate of reaction. So higher concentration means that there are more particles per unit volume. This means that there is an increased frequency of collisions and an increased rate of reaction. I know it's very repetitive, but that's the point. These answers are all very, very similar, and you are very likely to get at least one of these questions on your exams. Now, lastly, the one that's a bit different is catalysts. And catalysts are chemicals that we add to substances to increase the rate of reaction. That's all they're used for. They do not have an impact on the position of equilibrium. They do not have an impact on the yield itself. They just make the reaction happen more quickly. And they do this by lowering the activation energy. So on the graph, you can see there are 2 bumps. This is an energy level diagram that you should be aware of from your work in C1 on exothermic and endothermic reactions. This is an exothermic reaction because the products are at a lower energy level than the reactants. Now the blue line shows us the activation energy without a catalyst, and you can see that's quite high. So in order for the reactants to become the products, they have to overcome that energy. However, with a catalyst, we see that activation energy drops. And the way that happens is that we say that catalysts provide an alternative reaction pathway. Now, in a very short and very, very summarised way, catalysts work in a variety of different ways, but they can bring particles closer together to enable them to collide more easily. They can provide a surface for things to react on. They can do other things to molecules that makes them more likely to react, but you don't need to know any of that at your GCSE level. That becomes clearer at A level and at degree level. Catalysts. I'd like to pause the video now and explain to me how adding a catalyst can increase the rate of a reaction. Okay, so catalysts lower the activation energy by providing an alternative reaction pathway. This means a greater proportion of particles will be at or above the activation energy. This increases the rate of reaction. Now you have learnt about all of the different factors that affect rate of reaction, and they all follow a very similar pattern. You've got to talk about particles, you've got to talk about rate of reaction, and you've got to think about whether you're talking about simply frequency of collisions or you're talking about energy. Temperature and catalysts, you talk about energy. The others, you only talk about frequency of collisions. If you mention energy in those questions, you will get no marks because it's simply not true. Let's move on then. So that is how you can affect the rate of a reaction. What we now want to look at is how we can measure that in the exam. Now, in the tick list on the right, there are very clear points about being able to calculate the mean rate of reaction and interpret graphs. Now, when you get a graph for rate of reaction, you are always going to have time on your axis. And that's because rate, by definition, is something over time. And on your y-axis, you'll either have volume of gas produced or the mass of reactant, and that would mean it would go down. And there are 2 types of questions that you can be asked about rate of reaction using these graphs. Now, the first one is where you're asked for mean rate. Now, mean rate, the question will always say something along the lines of, what is the rate after this amount of time? And in that case, what you need to do is you need to go up to that amount of time on your line and work out what the volume of gas and the time is at that particular, after that point, and then use your equation which we looked at earlier, which is rate of reactant used or product formed divided by time. Now that's quite simple. You just go up to the graph after they've given you the specific time. However, that is about an average, because as you can see, from 0 up to that point on this first graph, that is a curved line. So we're taking an average there because the rate isn't equal all the way along that line. Example 2 is something that's a little bit more difficult, and this is higher tier only. Here it asks you to calculate the rate at 20 seconds. And you need to be really clear that if the question says at a certain time, then that is when they're asking you for specific rate of reaction at a specified time. And in that case, you need to draw a tangent at 20. And all a tangent is, and you should know from maths, is a straight line against the curve at the specific time they've quoted. Then you would work out the gradient, as you would normally do, of a line using the values on that graph. Now, you will be given more marks for ones that you have to work out a tangent for. Now, I'm not going to ask you to do these now because they're far easier to do when you have them on paper in front of you. So that completes most of these first points on the tick list. What we now need to move on to is what a reversible reaction is. Now, this seems to be something that people put down as things that they find most difficult. But actually, reversible reactions are very, very simple. So in general, the reaction in front of you is a reversible reaction. And we can tell straight away that this is a reversible reaction because it has the reversible reaction sign. And that's this in the middle here, the two half arrows. So this is a general equation. You have your reactants A and B producing C and D, which are your products. But equally, because it's a reversible reaction, at the same time, C and D will be reacting together to form A and B. Now, when these are at equilibrium, both things will be happening. Okay, so whilst you might have A and B forming C and D, it's going to, at the same time, if the conditions aren't correct, C and D are going to react to form your starting product. Again, now reversible reactions are really, really common. And one of the most common ones that you hear about frequently is the Haber process that we will talk about later on. Now, the Haber process is triple only, so we'll start first of all by just talking through some of the examples they want you to know. But one thing that you must know about reversible reactions is that this little fact down the bottom. If a reaction is exothermic in one direction, it will be endothermic in the other. So let's imagine that when we react A and B together to form C and D, that heat is released. That means in order for C and D to react together to form A and B, heat must be absorbed because that would be an endothermic reaction. And that's really important when we start to look at Le Chatelier's principle later on. We need to understand that exo in one direction means endo in the other. Now, one of the things that your exam board asks you to be able to do is to identify examples of this. Now, first of all, the first most common example that we can think of when we think of reversible reactions, is the reaction of hydrated copper sulfate. Now, I have a video of this that I will include so that you can see it. Now, hydrated copper sulfate is a lovely blue complex. It's formed in these blue crystals. They are soluble as well. You can dissolve them in extra water so that you get this really vibrant blue solution. And the equation for that you can see below. And where it says CuSO4.5H2O, that means that 5 waters are coordinated to it. Again, you don't need to know that too much at this level, but when you move further in chemistry, you may need to. Now, the forward reaction in this case is an endothermic reaction. So in order to form anhydrous copper sulfate, what we need to do is heat it up. So when you heat hydrated copper sulfate, you form anhydrous copper sulfate. And steam, that water sort of detaches itself from the copper sulfate and forms steam and evaporates. And you're left with this really, really white, powdery substance. It's very different in terms of its structure to hydrated copper sulfate. Now, in order to get anhydrous copper sulfate back to hydrated copper sulfate, you're going to add some water. You're going to add those 5 H2Os. And what you see is it goes back to this blue substance. I can then heat it up again, turn it back into the white substance. You can go forward and back, and that shows you that it's an exothermic reaction. That shows you that it's a reversible reaction. Now, number 2 shows us a second one. Now, this one's slightly more difficult because it's hard for us to recreate in the lab. Now, ammonium chloride is this white solid here. Ammonium chloride is a salt, and when heated, it decomposes into ammonia and hydrogen chloride. And both of those two things are naturally gases. Now, hydrogen chloride is not a nice gas. It's not something that you can have in the lab, hence why we haven't done it at school. Now, like I said, heating ammonium chloride causes it to decompose into ammonia and hydrogen chloride. However, if I allow those two gases to get cool enough, what happens is that they bond and form the white solid again. So those are the 2 examples that the exam board want you explicitly to know for the combined syllabus. Now, like I say, on the triple syllabus, you also need to know about the Haber process, but we'll follow that up in a second. In fact, we'll follow that up in a separate video. Now, what we now need to look at is what equilibrium is. So we've talked about reversible reactions, and we use the word equilibrium to describe the state of those reversible reactions. And particularly the phrase dynamic equilibrium is one which comes up frequently. Now, dynamic simply means it's moving, and that means that equilibrium is shifting. An equilibrium refers to things in balance in general. So if I were to hold a stretch and I were at equilibrium, we would normally sort of describe that as me being stable and still. Now, I want you to try and think of your definition for equilibrium. If we feel confident enough to, I'd like us to pause the video here and have a go. If not, I have got some sentence starters, a little close activity for you to have a go at. So in a something system, the something of the forward reaction is something to the something of the reverse reaction. I would like you to now have a go at that statement. Okay, so what we should have written down is that in a closed system, the rate of the forward reaction is equal to the rate of the reverse or backward reaction, depending on how you want to write it. Now, 2 marks for that question, 1 mark for that closed system. Remember, a closed system is one where energy can move into and out of the system, but matter cannot. And what that means in chemistry, I suppose practically, is that you've got a situation where you have a lid on your experimental system, so that no gases can escape, basically, because that will obviously affect the rate of reaction. Now, this is the content that I have covered in this little session, and what I want to leave you with is 2 exam questions. So what we've got up to is this point here. What we will then move on to is Le Chatelier's principle and the Haber process. Before we do that, we're going to have a look at some exam questions. So this first question, the rate of reaction when manganese dioxide is different when used as a fine powder rather than coarse lumps. Explain why. You should answer in terms of collision theory. Now, the first thing you need to do is look at fine powder and coarse lumps. Which of those different factors are we talking about when we refer to these things? It's only worth 2 marks, so be sure to explain how the reaction is different and explain why. Pause the video now and have a go at an answer. So, the mark scheme is very clear. Because surface area of fine manganese dioxide powder is greater, there are more collisions per unit time. Now, you can say the word frequent collisions here because that means the same thing. In some questions, you would have a 3rd mark here describing how the rate of reaction would increase. I think they have been probably a little bit harsh here in terms of only giving these 2 as your points, but it is only a 2-mark question. If you said that the surface area was smaller for coarse lumps, that would also be fine. It's very clear that you are not to write about energy because we're talking about surface area, nothing else. And also about speed, because that's related to the energy. If we think back to our physics work, we know that energy, kinetic energy, we can use to derive the speed. Also asks us to ignore activation energy. Now, our second question, based on what we've done today, is about reversible reactions and chemical equilibrium. And this one is worth 3 marks. So the first question, reversible reactions can reach equilibrium in a closed system. What is meant by a closed system? This is a 1-mark answer. It's a very simple definition. Step 2, explain why when a reversible reaction reaches equilibrium, the reaction appears to have stopped. Now this one takes a little bit more thinking. It's explain why. So think about what we mean by saying something has reached equilibrium. Think back to what we've just talked about. And then think about why that might appear that the reaction has stopped. It's 2 marks, 3 marks in total. So we would normally give 3 minutes for this. I want you to pause the video now and have a go at that. So you should now have had a go at this question. And now we're going to look at the mark scheme. So the mark scheme here, first of all, for your definition of a closed system, nothing can enter and nothing can leave the reaction. The idea that you have a sealed reaction vessel. And that's really important because that's why it works. That's why this makes sense, because we can't add any extra reagents and we can't remove any of the products that we're making. Now the second question, why does it appear like nothing is happening, or why does it appear the reaction has stopped? But because the forward and backward reactions have the same rate in equilibrium, that means that your A and B are reacting to make C and D at the exact same rate that C and D are making A and B, there's no overall change in the quantities of reactants and products. We could also use the word concentrations there. That makes sense, because the rate at which I convert A and B to C and D is the same at the rate at which I convert C and D back to A and B. Give yourself a mark out of 5 for that. These are questions that come from past papers. They are not things I have made up, so they're really good if you've managed to get those done. So that's the end of this video. You have looked at the first half of this section, and in the next video we will talk about the higher tier Le Chatelier's principle, and we will talk about the triple content, which is the Haber process.